Hello, future math experts! Welcome to our first chapter on advanced differentiation. Today, we are diving into algebraic powers and radicals. To get us started, look at that magnifying glass in the center. We call this the optical zoom analogy. Imagine you are looking at a curved line. As you zoom in closer and closer, that curve starts to look like a straight line. That straight line is what we call the tangent, and its slope is the derivative. In this chapter, we have four big goals. 1. Master the derivation of generalized powers, even when the exponent isn't a simple whole number. 2. Learn how to tame those scary-looking nested radicals, roots inside roots, by using fractional exponents. 3. Rigorously analyze if a function can actually be derived at its boundaries. It's not always possible. 4. Learn the art of simplification, so your final answers look elegant and are easy to use. Let's start this journey together with confidence. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content.
Let's think of differentiation as a mathematical microscope. Look at the graph on the left. When we zoom in on a smooth point, something magical happens. The curve reveals its local straight line, which is the tangent. The slope of this line is exactly what the derivative represents. Now, look at the graph on the right. When we zoom in on a boundary point, like the start of a square root curve, the slope becomes infinitely steep. It's a vertical line. At this exact spot, our usual linear approximation fails because the slope is infinite. This chapter is going to give you the exact algebraic tools you need to manage these chaotic boundary points and transform complex derivatives into simple, usable forms. You've got this.
Now, let's look at the heart of our calculations, the power rule for generalized powers. The rule you already know for integers works for all real numbers, even fractions, negatives, or even pi. The derivative of x raised to the power of r is simply r times x raised to the power of r minus 1. Why? Because we can rewrite x to the power of r as e raised to the r times natural log of x. Using the chain rule on that gives us our familiar formula. But beware of the domain trap. We have three cases. 1. If r is 1 or greater, the function is smooth and differentiable at 0. The derivative is 0. 2. If r is between 0 and 1, like a square root, the function is defined at 0, but not differentiable there. Why? Because the derivative will have a negative exponent, which means you'd be dividing by 0. 3. If r is negative, the function isn't even defined at 0. Always check your domain before you start calculating. Do you see those monster nested radicals? Don't let them scare you. The secret to taming them is our golden rule. The nth root of u is just u raised to the power of 1 over n. Never try to derive these directly. Instead, convert them to fractional powers from the inside out. Let's look at f of x equals the square root of x times the square root of x times the square root of x. Step 1. Handle the innermost root. X times the square root of x is x to the 1 times x to the 1/2, which is x to the 3 over 2. Step 2. Take the next root. X to the 3 over 2 to the 1/2 is x to the 3/4. Step 3. Multiply by the outer x. X to the 1 times x to the 3/4 is x to the 7/4. Step 4. Apply the final outer root. X to the 7/4 to the 1/2 is x to the 7/8. Now, deriving is child's play. Just apply the power rule to get 7 over 8 times x to the negative 1/8.
This is how you turn a monster into a simple kitten.
Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content.
Sometimes formulas aren't enough. We need the mathematician's eye to check boundaries. We use the rate of change limit. If the limit of f of a plus h minus f of a over h as h approaches 0 is a finite number, the function is differentiable. If it's infinite, we have a vertical tangent, and it is not differentiable. Let's test g of x equals square root of x squared plus square root of x at x equals 0. We set up the limit as h approaching 0 from the right. We bring h inside the root as h squared. This simplifies to the square root of 1 plus 1 over h times square root of h. As h gets tiny, that fraction inside blows up to infinity. Since the limit is infinite, the function has a vertical tangent at 0 and is not differentiable there. This limit test is your ultimate truth detector.
Welcome to the art of simplification. Often, your raw derivative looks like a mille-feuille, a messy stack of fractions that's impossible to study. If you can't tell if the result is positive or negative, it's useless. Follow these 3 steps. 1. Identify the common denominator, which is usually the radical part. 2. Multiply those isolated terms by that radical to merge the fractions together. 3. Factor the top to group polynomials together, leaving one single radical on the bottom. Look at our example. Y prime equals 3x squared plus 1 over 2 square root x plus 2x square root x. By multiplying the second term by 2 square root x over 2 square root x, we get a common denominator. This merges into 7x squared plus 1 over 2 square root x. Now it's clean, compact, and we can easily see it's always positive. Beautiful, isn't it? Exercise 1. Complete study of f of x equals the cube root of x squared times x minus 1. The mission: 1. Determine domain of definition. 2. Study differentiability at boundary points x equals 0 and x equals 1. 3. Calculate derivative and simplify to a single root. Data and unknowns. Function: cube root of a polynomial. Goal: limits of difference quotients and algebraic derivation. The strategy: for Q1, cube roots accept all real numbers. For Q2, use the limit as h approaches 0 of f of a plus h minus f of a divided by h definition. Expect infinite limits at the roots of the inner polynomial. For Q3, convert cube root of u to u to the 1/3 before applying the chain rule. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Let's solve the first part of our exercise. Step 1. The domain. Since it's a cube root, it's defined everywhere, so the domain is all real numbers. Step 2. Differentiability at x equals 0. We set up the limit of f of h over h. By rewriting h as the cube root of h cubed, we can merge everything into one radical. The result is the cube root of h minus 1 over h. As h goes to 0 from the left, it goes to plus infinity. From the right, minus infinity. This means we have a cusp with a vertical tangent, not differentiable. Step 3. Differentiability at x equals 1. We do the same limit setup.
After simplifying, we get the cube root of h 1 plus h squared over h minus 1 cubed. This again goes to plus or minus infinity. So at x equals 1, we also have a vertical tangent and no differentiability. Even if a function is defined everywhere, it can still have sharp points where the derivative doesn't exist.
Now, let's find the derivative for everything except those boundary points 0 and 1. Step 1. Turn the cube root into a fractional power, x cubed minus x squared to the power of 1/3. Step 2. Apply the chain rule. The 1/3 comes down, the exponent becomes negative 2/3, and we multiply by the derivative of the inside, 3x squared minus 2x. Step 3. Restructure it as a fraction. This puts our original term squared in the denominator under a cube root. Step 4. Algebraic simplification. Notice we have an x on top and an x hidden in the bottom. By canceling them out, simplifying the isolated x terms, we reach our final optimal form, 3x minus 2 divided by 3 times the cube root of x times x minus 1 squared. This is perfectly simplified and ready for further study. In exercise 2, we tackle nested square roots. G of x equals the square root of x plus square root x. Our mission is to find the derivative and express it as a single quotient. The strategy here is to apply the radical rule. Square root of u equals u prime divided by 2 square root u from the outside in. Let's prepare our components first. The inner function u of x is x plus square root x. Now let's find its derivative, u prime of x. It's 1 plus 1 over 2 square root x. Here's a pro tip. Create a common denominator for u prime of x early. It becomes 2 square root x plus 1 divided by 2 square root x. Having this ready will make the final assembly much smoother. You're doing great. Keep going. Now for the assembly and final polish of exercise 2. We plug our components into the formula u prime divided by 2 root u. This gives us a fraction on top of a radical. To simplify, we combine the denominators, which gives us 2 root x plus 1 divided by 4 root x times the square root of x plus root x plus 1. But wait, we can do better. Notice the root x outside and the root next to it. We can bring the root x inside that adjacent root by squaring it. It becomes x. So root x times square root of x plus root x plus 1 becomes square root of x squared plus x root x plus 1. Our final answer is 2 root x plus 1 divided by 4 times the square root of x squared plus x root x plus 1. Look at that. No superimposed radicals on the bottom. It's clean, professional, and ready for sign analysis. Great job. Exercise 3 presents a rational-irrational hybrid. We need to derive h of x equals x minus 1 divided by square root of x squared plus 1. Because it's a fraction, we use the quotient rule. U over v prime equals u prime v minus uv prime divided by v squared. Let's set it up. U is x minus 1, so u prime is 1. V is the square root part, so using our shortcut, v prime is 2x divided by 2 square root of x squared plus 1, which simplifies to x divided by square root of x squared plus 1. Now, when we apply the rule, the numerator becomes a messy milfoil of fractions. Don't panic. The warning sign is there for a reason. We must simplify this immediately before we get lost in the algebra. Let's clean it up in the next step. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. The final step for exercise 3 is the most crucial, clearing the numerator. We have a fraction inside our big numerator. To fix this, multiply the entire top expression by square root of x squared plus 1. This clears the internal fraction. The top becomes x squared plus 1 minus x times x minus 1, which simplifies beautifully to just x plus 1 over the radical. Now, for the final assembly, we put this back over our original v squared, which is just x squared plus 1. By combining the powers, our final answer is h prime of x equals x plus 1 divided by the square root of x squared plus 1 cubed. Now look how easy this is to study. The denominator is always positive, so the sign of the whole derivative depends only on x plus 1. Mastery achieved. Let's summarize everything we've learned in this core concept synthesis. 1. Generalized powers. F of x equals x to the r is differentiable on the interval from 0 to infinity for all real r. 2. Difference quotient. This limit is your best friend for determining if a function is actually differentiable at its boundaries. 3. Vertical tangents. If that limit goes to infinity, you have a geometric non-differentiability. The curve is just too steep there. 4. Nested radicals. You must convert these to fractional powers before you even think about deriving. 5. Optimal form. Your ultimate algebraic goal is to reach a single fraction with a radical on the bottom. Why? Because it makes studying the sign and finding where the function increases or decreases totally trivial. This table is your roadmap to success. To wrap up Chapter 1, here is some master's advice on common pitfalls. First, avoid the millefeuille error. Don't stop your calculation when it's a messy sum of fractions. Always find a common denominator. Second, watch out for the nested trap. Never apply rules directly to roots inside roots. Rewrite them with exponents first. Finally, the pro tip. Always step back and think about the domain of differentiability before you start mechanical calculations. Remember the optical zoom. It breaks at sharp points and boundaries. Validate your limits first. You've worked hard and learned some powerful techniques today. Keep practicing, and I'll see you in Chapter 2. You're becoming a real math star.